Hello everyone, I'm Zhou from Tsinghua University. Today I'm going to talk about our work on fast software cache design for network appliances. This is a joint work with my collaborators Huacheng, Michael, and Dave. The driving application for our work is the use of flow caching in Open vSwitch. As many of you might already know, Open vSwitch is one of the most popular software switches and has wide production deployment. It achieves great performance through extensive flow caching. Specifically, there are 3 layers in its caching hierarchy. When a packet is received by the Open vSwitch, it is first lookup in a layer called microflow cache. This microflow cache does an exact match using a single cache table. It maps the connection or the microflow to the corresponding action the Open vSwitch should take upon these connection. If the packet is missed from the microflow cache, it will be then looked up in the megaflow cache. This megaflow cache does wildcard match but without priority, and it is implemented with multiple masked cache tables. So here I show you a couple of rules in the stored in the megaflow cache, where we have some wildcard match in the rule, but because the megaflow cache does not support priority, all the rules are guaranteed to be destroyed. So there will be no ambiguity when match a packet against these rules. If the packet is again missed from the megaflow cache, it will be looked up in the packet classifier, which matches the packet against a bunch of open flow rules. Here I show you two match conditions and their corresponding actions. So it's quite obvious that because every packet is first looked up in the microflow cache, and the megaflow cache is simply much slower compared to the microflow cache. And our experiment verified that a megaflow cache lookup, which is the cost you're going to pay if you missed from the microflow cache, could be 8x more expensive compared with a microflow cache lookup. So that's why the microflow cache hit rate is critical to the overall performance of Open vSwitch. On the other hand, however, because again, every single packet is first looked up in the microflow cache, its lookup latency also matters, right? If it's slowed down by 20%, then the entire throughput of the Open vSwitch is going to be slowed down by that much. So we want the microflow cache to have high cache hit rate and low lookup latency at the same time. And these two seemingly conflicting requirements create an interesting problem for the design of microflow cache. So let's start with some basic design for the microflow cache, and gradually we'll introduce different ways to improve it, and finally I will reveal our design for the microflow cache. So let's start with the set-associative cache. Here on the slide, I show an example of a 4-way set-associative cache where each bucket is 4-way set-associative. When a packet with the header K arrives at the Open vSwitch, we can use a single hash function H to map K to one of the bucket HK. Then we can compare K against all the keys stored in the bucket. If there is an entry with the matching key, we can return the corresponding value. Otherwise, we claim it is a cache miss. Okay? And when the cache misses and there is no free slot in the cache table in the bucket, we have to pick a victim and evict the victim to put K in its spot. So this sounds pretty simple, but what kind of cache hit rate this simple design can give us? So to understand this problem, we define the oversubscription factor alpha for cache as the number of keys divided by the number of values. In other words, it represents how crowded the working set is, how large the working set is compared with the total capacity for in the cache. Okay, we assume a uniform workload, and we use random eviction as our eviction policy. So for alpha equals to 0.95, which means the working set is just slightly smaller than the total entries in the cache. This simple four-way set-associative cache give us a cache key rate of around 81%. So this is not good at all, because that means 20% of the packet. That means if we use this cache design, right, then 20% of the packet will be missed in the microflow cache, even though we have enough space to cache all of them. So we need to find something better. A simple way to improve the cache key rate is to increase the set-associativity. This is just conventional wisdom. We learned that from the hardware cache design and a lot of other places. The core idea here is to increase the set-associativity of each bucket. For example, we can increase it from 4 to 8. And then because we want to use the same amount of space, we have to reduce the number of buckets by 50%. So now we have a 8-way set-associative cache instead of a 4-way set-associative cache. To look up in this cache, we still use the same hash function hk to map the key to one of the buckets. But this time, instead of comparing with 4 keys in the previous bucket, we can compare it against 8 keys, which means we can have a little bit more freedom for the key. So this simple change increased the cache key rate from 81 to 87%, which is pretty good. But still, we have about 13% of the packet will miss from the cache. So another way to increase the cache key rate is to use not only one but 2 hash functions. For example, to look up a key k, we can use h1k and h2k to find 2 different buckets for k. Okay, now to look up a key k, we can compare it against all the 8 keys in h1k or h2k. Okay, if there's any matching key, we return the corresponding value. Otherwise, we can pick a random victim from any one of the 2 buckets and make a room for k. So this is inspired by cuckoo hashing, and it achieves an amazing cache key rate of 99%. But what could so this sounds good, right? But this cache still has a drawback, and the drawback is that compared with the 4-way or 8-way set-associative cache, not every lookup in this new cache design will have to access 2 different cache lines, right? That put more pressure on the memory subsystem, especially when the packet throughput is high, and therefore slow down the lookup latency. And that is not what we want, because as we stated earlier in the talk, one of the goals we want to achieve in the cache is low lookup latency. So how could we solve this problem by increasing the cache key rate but not lookup latency? To address this issue, we propose a new cache design called bounded linear probing, or BLP for short. So it uses the same structure as the 4-way set-associative cache. To look up a key k in BLP, you use the single hash function hk to map it to the same bucket, to a single bucket. Now, the difference between BLP and a simple 4-way set-associative cache is that instead of only allowing k to reside in hk, we allow it to be spilled over to the next bucket. So in this example, the key k can be placed in any one of the blue-colored slots. Okay, if we have another key k prime that maps to the next bucket, then both k and k prime can be stored in this overlapped bucket. So intuitively, this overlapping gives us the ability to kick keys around and make room for keys, right? If there is one particular bucket that has many keys mapped to it, we can kick it to the next bucket. And then if the next bucket is also full, we can kick them to their next bucket, so on and so forth. Because we use four-way set-associative bucket, and each key can be stored in one of the two consecutive buckets, this particular data structure is called 2,4-BLP. And in our paper, we show you that this simple change increased the cache key rate from 81 to about 94%. So this is a pretty big jump. So if we compare the four designs we just talked about, there are two sets of comparisons that really interest us. The first one is 8-way set-associative cache and the 2,4-BLP. So compare with 8-way set-associative cache, 2,4-BLP use 1.5 consecutive cache line reads, but increase the cache key rate by about 7%. So why is that the case? Why BLP can store more entries than set-associative cache? So to understand this, this question, I draw you an example on the slide. So each row represents a bucket in the cache, in the 4-way set-associative cache. If we simply use a 8-way set-associative cache, what we can see is that only bucket 2 and bucket 3 can store in the new bucket 1, right? And the bucket 0 and 1 can store in the new bucket 0, so on and so forth. And this 8-way set-associative cache give us a occupancy of about 71.8%. In contrast, if we use 4-way BLP to store this data set, then we can get a occupancy of 75%. And the reason is that, as I just said, some of the flexibility of the BLP allows us to kick the keys around. For example, in this case, the two keys that was mapped to bucket 3 are now entirely stored in bucket 4. Okay, so you can never do this with the 8-way set-associative cache. That's the fundamental reason why the BLP has higher cache key rate than the set-associative cache. Now, comparing the 2,4-BLP against the 2,4-cuckoo, what we can notice is that 2,4-BLP replaced the 2 random cache line reads that is required by 2,4-cuckoo with 1.5 consecutive cache line read at a cost of about 5% cache key rate. So this is an interesting trade-off because it sacrificed the cache key rate a little bit, but on the other hand, it increased the lookup it improved the lookup latency. So as I will show you later in this talk, this trade-off makes sense for the case of OVS because the packet rate is just very high, and the increased key rate of 2,4-BLP is not enough to compensate for the long latency, the long lookup latency of that data structure. So we just talked about the table design. Another important issue in designing a cache is a cache replacement policy, and this is roughly orthogonal to the table design itself. So far, we have only talked about the random eviction, right? But when the workload is skewed, random eviction obviously cannot give you the best cache key rate. Traditional designs such as LRU are very costly to implement. They require storing additional informations, and just maintaining those informations requires more CPU cycles and additional space. So even some approximation of LRU, such as clock, requires 1 bit per extra key, and this is not what we want in microflow cache, because all the memory layout are well aligned, and we cannot afford this additional space. To address this problem, we come up with a new cache replacement policy called Probabilistic Bubble LRU, or PBLRU for short. So at its core, the PBLRU used a operation called bubbling to organize entries within the bucket. Here I show an example where A, B, C, and D are stored in the same bucket. Okay. Now, if we look up a key D, we first use the hash function H to map D to the bucket, and we notice that D is the last entry in the bucket. So what do? We swap D with its predecessor in the bucket, in this case C. So then to reflect the reality that D is recently accessed, and we call this operation promotion. Okay. This time when we look up another key X that maps to the same bucket by the hash function, but X is not in the bucket. So we have to find a victim for X. Instead of randomly pick a victim, we always replace the last entry in the bucket with the key X. And this operation is called eviction. So in other words, what's essentially happening here is that we assign a different priority for different slots in the bucket. The first bucket has the highest priority. The second bucket has the second highest priority, and the fourth bucket has the least priority. And when we have to pick a victim, we always pick the one with the least priority. So this basically bubbling can combine both the recency and frequency information, right? We talk about the recency, and frequency is also quite easy to understand. If you access a key multiple times, it will guarantee to be stored in the front of the bucket. But this basic bubble LRU still has some high cost in terms of memory writes, because every time if we have a cache hit, you have to swap two consecutive entries in the bucket, and that requires a memory write. To solve this issue, we use a technique called probabilistic bubbling, which simply means we only promote a key on every nth cache hit to reduce the number of memory writes. So intuitively, this won't hurt the accuracy, because for more frequently accessed keys, it will still get a chance to be promoted. Another issue to apply the PBLRU to BLP is that in BLP, so PBLRU only works within a single bucket, right? And when you use BLP, each key can be mapped to two consecutive buckets. So when we try to find a victim, you will have two different candidate buckets, right? So to address this issue, instead of doing more complicated computation, we simply use a random bucket to apply bubbling if the key is missed from the bucket. So to evaluate the effectiveness of BLP and the PBLRU, we applied them to Open vSwitch and measured the end-to-end throughput of the Open vSwitch using two Cloud Lab machines. For the first set of experiments, I'd like to share with you the end-to-end throughput of our Open vSwitch deployment. The x-axis here is the oversubscription factor from 0.5 to 2. So the smaller the oversubscription factor, the emptier the cache table is. So and the y-axis here is the end-to-end throughput measured in million packets per second. So when the oversubscription factor is low, we can cache more entries in the table, and that's why the throughput is high. So as we can clearly see from the figure, the orange line, which represents the 2-for BLP, achieves the best overall performance for the uniform workload. And the improvement over alternative designs could be as high as 15%. To understand why this is the case, we break down the experiments and measured the lookup latency in terms of CPU cycles and the cache key rate of all the cache designs. So on the left, on the left side shows the lookup latency. So the smaller is better. As we can clearly see, the 2-for cuckoo has much higher latency compared with alternative designs. And the reason for that, as we explained, is that every lookup in the 2-for cuckoo requires 2 distant memory fetches instead of 1. 2-for BLP uses 1.5 consecutive cache line reads, so it is slightly slower than the set-associative cache, but much faster than 2-for cuckoo. On the right-hand side is the cache hit rate. So the higher is better. And 2-for cuckoo does have the highest cache hit rate among all the cache designs, but because it's high lookup latency, its overall performance is worse than the 2-for BLP. In other words, the cache hit rate improvement of the 2-for cuckoo is not enough to compensate for its high lookup latency. For the second set of experiments, we show you the end-to-end throughput of the skewed workload. And again, the x-axis here is the overall substitution factor, and the y-axis is the end-to-end throughput. So when the workload is skewed, 2-for BLP with Bubble LRU achieves the highest throughput among all the designs, and it is 75% higher than the alternative designs. And again, we break down the lookup latency and the cache hit rate. We can it's clear that the BrdgAI improved the cache hit rate at a very low extra cost if we compare the gray line and the orange line on the left side, right? So the gray line is 2-for BLP with PBLRU. So it is slightly slower than the orange line, but it achieves the higher cache hit rate. So to summarize, in this talk, I tell you 2 interesting techniques: bounded linear probing and probabilistic Bubble LRU. And we combine those 2 techniques to build a fast microflow cache in Open vSwitch. And the core idea behind those 2 techniques are the same. That is, we want to balance between the cache hit rate and the lookup latency. So either if you want to have extremely high cache hit rate, but at a sacrifice at the lookup latency, or the other way around, won't give you the best overall performance. And I think that's the main takeaway of this talk. That's all I have for you. Thank you very much.